Okay, first the announcement. If you know him, or if he's here, just you should go and see the department secretary. They are looking for you. They have been looking for you all day long, and you just cannot believe how many messages they sent me to send this message to you. Okay, so before we continue with physics questions, if you remember, the last thing we were discussing were oscillations, and today we will be continuing with oscillations. Now, any questions about the oscillations or oscillating systems? Now, if you remember, on Tuesday we were looking at, first we studied somewhat the elasticity. We said that in fact, everything to a limited extent would obey the Hooke's law, whether it is this object, a solid object, or a spring, they will follow Hooke's law to a limited extent. And if you have an object that follows the Hooke's law, for example, you have this spring, at the end of which you attach a mass m. This has a spring constant k, and let's assume that this is at equilibrium. This is its equilibrium position, and if you just displace it slightly and release it, let's say this is x, it is the time dependence of its position will be, you can determine the equation that it will satisfy from Newton's second law, which just tells us that the m times a should be equal to minus k times x, or m times the second derivative of x is equal to minus k by x itself. Whenever you see this equation, you should immediately tell that the x is a harmonic function of time, which means that x can be written as a times cosine omega t plus phi, where this a is called the amplitude, omega is the angular frequency, and this phi is called the phase shift. It's just the terminology we will be using. Now this is basically what we had done. Now any questions on this up to here? What is the phase shift? Well, if you look at the function without the phase shift, let us plot it. Okay. So let us plot this function first. This is cosine omega t. This is phi is equal to 0. Let me make an exact copy of it. As you increase phi, you see this function has a maximum when, if phi is 0, the cosine has a maximum when its argument is 0. If phi is, let's say, positive, then this cosine will still have its maximum when its full argument is 0, but that means when omega t is minus phi. If phi is positive, it will have a maximum when it is negative. So this orange curve corresponds to phi larger than 0. So it basically shifts this shape in time. Well, you can also write it like this. Phi, let's say omega times t0. T0 is some new unknown. Then x is equal to a cosine omega, no, let's say minus omega t0, t minus t0. But phi basically determines your origin in time. So which point on this axis do you call t equal to 0? If you change phi, you are basically changing that definition. Now, from this equation, this is what is called the differential equation. You will be studying differential equations next year. So quite often I get the question, how do you drive this solution to this equation? Well, you will see also next year, or even if you study some higher differential theory in mathematics department, that you don't. There's no derivation from here to this one. You just know that if you have a differential equation with constant coefficient, the solutions are cosines and sines. That's just trial and error, in a sense. So the x should be such a function that its derivatives should be equal to itself, and there are not many functions that you know. One is the exponential function, one is the cosine and the sine functions, which when you take the derivative, they transform into themselves. So that's basically what we are also doing here. Now, any questions? Now, before studying this motion in more detail, let's look at one more example in which is also described by exactly the same equation. Let's look at this object. Okay, so if I just lift it to one side and release it, this will be the motion. It's again an oscillatory motion. Now let's study the motion. It's not a point object. It's in fact, this object will be rotating around this point. So let's say this is my rigid object. I fix it, it is rotating around this point. Let's say this is the position of the center of mass. This is the center of mass position over here. And let's consider this angle, this line connecting the rotation axis to the center of mass, and then we can define this coordinate, this angle theta. So if we know this angle theta, in that case we know what the orientation of my object is. Now then, since this is rotating around this point, the angular frequency is, in terms of theta, it's just the time derivative of theta. This is at least the angular speed, let's say. The angular acceleration, its magnitude, would be this one. We can express all the angular acceleration in terms of theta. Now, what about the vector? Let's look at the vector, because the directions will also be important. Let's say this vector z. Now, the angular velocity, okay, on one hand it is d theta by dt. Is it plus z or minus z? I don't know. I mean, this is the question. So let's say you know somehow how theta, this angle theta changes with time, and then you want to write the angular velocity vector. This is the information you have. You don't need to know whether it is rotating clockwise or counterclockwise. That's not a necessary information. Positive z. What if it's rotating in the other sense, in the other direction? Okay. So is this definition always true, or should I add a minus sign if the theta by dt is negative? Okay, so? Well, this is always true whether theta is positive or negative. Well, you can just, well, the theta by dt, there are basically two possible signs of it. If the theta by dt is positive, that means theta is increasing with time. Well, if theta is increasing with time, then my rigid object is rotating in the counterclockwise sense. Well, if it is rotating in the counterclockwise sense, the velocity vector should be in the positive z direction. The theta by dt is positive, and if I multiply it with the z hat, I obtain a vector in the positive z hat direction. So this is correct if the theta by dt is positive. If the theta by dt is negative, it just means that theta is decreasing with time. Well, if theta is decreasing with time, it means it is rotating in the clockwise sense, and hence the angular velocity is in the minus z direction. But if the theta by dt is a negative number, if you multiply z hat by that negative number, you obtain a vector in the minus z direction. So whether the theta by dt is negative or positive, this equality is always true. Of course, there's one thing you have to pay attention to. Theta is not necessarily a positive number. Theta is positive in this sense, it is negative in the other sense. If theta was some angle over here, then it's a negative number. Because if all this argument is true, it means that as the object is rotating in the clockwise sense, theta is decreasing, but after the center of mass moves in this direction, the magnitude of that angle is increasing. So if you still want to stick with the convention that theta is decreasing, theta has to be negative if it is somewhere over here. That is just something to keep in mind. So how can we determine the angular acceleration? This will be d squared theta by dt squared in the z hat direction. Now what will it depend on? What is this? Analog of the Newton's second law for rotationary motion. Well, the acceleration is equal to force or torque over I, the moment of inertia around this point. What is the torque acting on this system? Relative to the rotation axis. Since here we have a fixed rotation axis, we will be describing the motion in terms of rotations around that fixed axis. So what is the force creating this torque? What are the forces acting on the system to start with? There is the weight acting as if it is acting on the center of mass. What else? Weight is not the only force acting on this object. Well, the force at the suspension point. So it will be, what will be its direction? At this instant, let's say it is swinging down. Vertically up. Well, you see, the problem is, the acceleration of the center of mass is determined by the total force, always. So there is a weight acting in the downward direction. If this object is swinging in the clockwise sense, then the center of mass has an acceleration in the central direction and also tangential direction. So this acceleration of the center of mass is somewhere in this direction. Well, the total force has to be in that direction. There is a horizontal component to the total force. And that horizontal component should come from this force over here. So it will be, the force acting over here will be in some direction like this. It will have a horizontal component. It will be vertical component and also a horizontal component. Not necessarily along this line either. But. So what is the torque? What is the torque created by this force at this point? Zero. What is the torque created by the weight? First of all, what is the direction of that torque? Let's see, this is R, this is the force F, right? R, this is the direction of the force. R cross F is into the square. So it's in the minus z direction. What is the magnitude? Remember, this is the R vector that we use to calculate the torque. This angle over here is theta. Well, it is, let's say, this R times the weight times sine theta. So which basically tells us that d squared theta by dt squared is equal to minus mgr sine theta. Now what is dr by dt? Velocity. What is dr by dt? Here we say this is r. What is dr by dt? Well, we know that theta is changing with time. So does this change with time? Divided by I. Okay, back to the question, what is dr by dt? Somebody tell the velocity. Somebody else? What is r? What does r stand for in this question? Position, radius. It's just the distance between 2 points. It's the distance between this point and the position of the center of mass. It's not the position of anything. We just use the same symbol, bad notation in general. So since it's not the position of anything, it's not velocity. So, and this distance, since it's a rigid object, the distance between the center of mass and the suspension point doesn't change in time, so this is 0. If r was the position of an object, or the position vector of an object, then this would be the velocity, but not in this case, not in our definitions. R is the distance between this point and the center of mass. This is a rigid object. So the distances between any points on my rigid object is always the same. It doesn't change in time. So this is just a constant. The only thing that is changing with time in this equation is theta. So this is the equation that theta satisfies. Now the first thing that this equation tells me that theta is doesn't change harmonically with time. Theta is not equal to something times cosine of something else. So because if you have a harmonic motion always satisfies, if it was harmonic, it should satisfy this equation, minus omega squared theta. And we have shown that it doesn't satisfy such an equation, so it's not harmonic. Nevertheless, it is periodic. I mean, just observation tells you that it is periodic. It is oscillating back and forth. If there is no friction, it will be continuing indefinitely. It is periodic, but not harmonic. So that's also something to keep in mind. Whenever you see a periodic motion, it doesn't have to be harmonic. And this is an example of an unharmonic motion, oscillation. But let's see, what does the sine function look like? This is how it looks like, the sine function. Now, if you are very close to this point, it almost coincides with this line at this point. What is the slope of that line, which is tangent to this curve at this point? It's just plus 1. d by d theta sine theta at theta is equal to 0. This is just 1. So close in this region, the sine function and this straight line, whose equation is, let's say this is y, this is theta, y is equal to theta, this orange line. Orange line and this sine function in this circle, they almost overlap. So if theta is not big, that's if you look at this pendulum over here, if you just displace it by a very small angle, in that case sine theta is more or less equal to theta, approximately. And in fact, if you look at this angle, this point, they more or less overlap up to, let's say, around 45 degrees. Up to 45, 50 degrees, the deviation from theta is very small. So this is almost equal to minus mgr over I theta if theta is smaller than 1. By the way, 45 degrees, is it smaller than 1? "45 degrees is smaller than 1 if you think in terms of radians. So here you always have to think of in terms of radians. If you write theta in terms of radians, then the second derivative of theta is equal to this one, and sine of theta is approximately theta in terms of radians. But now we have this equation of the simple oscillator. And omega is equal to square root of mgr over I. So now we have seen that although this pendulum is not a harmonic oscillator, if we are sure that theta is small, in that case it is almost a harmonic oscillator. The motion the pendulum will do will be harmonic, and this will be the period. Now this is called the physical pendulum. Of course, if you want to be more realistic, you have to add the friction, etc. But this is, when you have such an object, this is a pendulum, this will be the equation governing its motion. Or even in this case, when you have some spherical mass attached to the end of a string, almost a massless string, a better treatment of this would be to treat this ball as a sphere which is displaced from the suspension point by a distance. So you know, by the parallel axis theorem, you know how to calculate its moment of inertia for rotations around this point also. Now, we can take the limit of the simple pendulum. Yes? Small angles. But it still gives a good enough description for angles up to 45 degrees, for example. Now, what we call a simple pendulum is we have a mass attached at the end of a spring, massless string. Now, the treatment is identically same. The only difference is the moment of inertia. What is the moment of inertia of this object? Yes, that's L. It's just a point object. I is ml squared. So the frequency of oscillations, we had already derived it. This is equal to square root of mg. Well, in this example, remember, r is the distance of this rotation point from the center of mass. So in this example, it's just L. mgl over ml squared. So omega is square root of g over L. So this is the period of a pendulum. At least theoretically, this should be the period of the pendulum. Now, the interesting thing is it only depends on g and L. So if you can measure the angular frequency of the pendulum, remember, if you measure the period was 2 pi over omega. So if you measure the period of oscillations, from that information you can determine the angular frequency. Once you know the angular frequency, and if you measure the length L, you can determine G. You can measure the gravitational acceleration at the point where you are. There is also another prediction that we can test, since if you are in a region, in a fixed region, then G is constant. So if you change L, this is how the angular frequency changes with L, or how the period changes with L. So the period is proportional to the square root of the length L. This is also another thing we can test. Well, let's give, and it also is independent of the mass. It should be independent of the mass. So if you just prepare two pendulums, both having the same length L, but they just differ in their mass, they should still have the same period. So these are the things that we can test with this setup. So this is basically, you have almost a point mass attached at the end of almost a massless string, and you can just change the position of this object so that you change the length and see how it changes with length. So let's start with a length equal to 9.9 centimeters. So the length is now 9.9 centimeters. Let's measure the period. So who is volunteering to keep 20 seconds? I need a timekeeper. Okay, you are keeping the time. And somebody should count how many oscillations it makes. Okay, you will be counting, somebody else also. You are also. You are also. So when you are ready, just keep 20 seconds. You will count how many times it goes. 1, 2. Okay? This is not 1. This one is 1. No. Okay, how many seconds? 9. Okay. So let's count just 5 seconds. So it's not a perfect pendulum. They should hear you. Okay, let's give it a second try. And they should hear that time is up. Okay, so are you ready? Okay, so 9 periods. T is equal to 5 seconds. So the period is 5/9 seconds. For a length L is equal to 9.91. Let me see. 9.91 centimeters. Let me change the length. Okay, now it's something around 20. You will repeat the same thing. 5 seconds. Okay, 6.5 periods is equal to 5 seconds, so one period is 5/6.5 seconds. So this is T1, this is T2. Let's look at the ratio. of T1 over T2. This is 6.5 over 9. And what is the calculator? This is 0.7. 0.7 is 1.4 over 2, which is square root of 2 over 2, which is 1 over square root of 2. Okay, this is square root of 2, square root of 3. I do advise you to learn them. Square root of 2 is 1.4, square root of 3 is 1.7, etc. Just a couple of them would be enough to simplify your life. So you see the ratio of the periods is 1 over square root of 2, but the length changed by a factor of 2. So this is kind of a simple verification that the period is proportional to the square root. If the length is larger, then the period became larger. For a larger length, we have a larger period. So the period is, experimentally now we have verified that the period is proportional to the square root of the length L. What is G? So remember, we know that T is equal to 2 pi square root of L over square root of G. Or G is equal to 4 pi squared L T squared over T squared. We know the numbers. If you don't have a calculator, so this should be approximately, let's see, when L was 10, period was 5 over 9, 4 pi squared 10 divided by 10 meters, 10 centimeters divided by 5 over 9 seconds squared. Pi is something like 3, pi squared is something like 10. This is 400 centimeters divided by 0.5 squared seconds squared. This is something like 0.4 meters per second squared divided by 0.5. 0.5. This is 2 meters per second squared. Do you agree? What does the calculator tell you? Okay, not such a precise measurement of G. But basically that's what we measure. No, this is 400 centimeters. You are right, this is 4 meters. So it's 20. Now it's better. And if you put the exact numbers, if your friends were saying that 15, the exact number is 12.6. Now this is much better at least. Of course, you have to add the error bars. The length is not exactly 9.91. The period is not exactly equal to this one because basically you are not measuring, you are going from 9 to 10. So this is the period is, here you have a 9.5 plus minus 0.5. So those are some errors that you should include. And if you calculate the error bars over here, you will see that it's in fact a much better in agreement with the actual value. Now, any questions on this? Okay, so let's continue with these oscillations, simple oscillations. And we know that the displacement, if we look at the one-dimensional analog, the displacement will be A times cosine omega t plus phi. What will be we know the velocity, and the speed is just the time derivative. This is minus A omega sine omega t plus phi. So we can calculate its kinetic energy. Kinetic energy of oscillation would be, if the mass is m, 1 over 2 m v squared. This is 1 over 2 m omega squared a squared sine squared omega t plus phi. This is the kinetic energy. But we also know the potential energy. This was 1 over 2 kx squared. This is 1 over 2 k a squared cosine squared omega t plus phi. But remember, omega squared was k over m, or k is m omega squared. So if you put m omega squared over there, this is 1 over 2 m omega squared a squared cosine squared omega t plus phi. This is the potential energy. Now if you compare the kinetic energy and the potential energy, this is the kinetic energy, some coefficient times sine squared omega t plus phi. The potential energy is the same thing multiplied by the cosine squared omega t plus phi. You can just add the two to obtain the total energy. 1 over 2 m omega squared a squared. So the total energy, in a sense, depends on the amplitude. Of course, this energy just oscillates between the kinetic energy and the potential energy. So if you just imagine that you take your pendulum, you displace it. This is the maximum displacement. The amplitude it's the maximum displacement. There is no kinetic energy. All of the energy is in the potential energy. When you release it, the potential energy starts to get smaller and smaller until it reaches this point. This is the point where it has the maximum kinetic energy. It has the maximum speed. So here, zero kinetic energy, maximum potential energy. Zero potential energy, maximum kinetic energy, and back to zero kinetic energy, maximum potential energy. So essentially, the energy just oscillates back and forth between kinetic and potential. So if this is the energy versus time graph, the total energy is constant. This is the total energy. Depending on at which time you choose as your zero time. Okay, let's say initially the potential energy is maximum, it goes to zero, maximum again, zero, maximum again. This is the potential energy. And the kinetic energy is initially zero, then it's maximum, minimum, maximum, minimum. So this is basically how the kinetic and the potential energies, they will also change in time. They are also harmonic. So kinetic energy was 1 over 2 m omega squared a squared sine squared omega t plus phi. This is equal to 1 over 2 m omega squared. Well, sine squared you can write as 1 minus cosine twice omega t. Let me write it below. This is equal to 1 over 2 m omega squared a squared 1 over 2 1 minus cosine twice omega t plus twice phi. And so it's also a harmonic function with twice the period.
This graph is critically for harmonic motion.
Well, this is what happens in harmonic motion, let's say.
Yeah. In this example, if the angle is too large, you said that it cannot be harmonic.
It will not be harmonic.
If there is no gravitation,
Then there is no torque, there is no angular acceleration. There is no periodic motion. Now, if the angle is large, it will definitely not be harmonic. The period will depend on the amplitude. Now, that's also another thing we could have tested, but we didn't. I mean, if you have such an amplitude or a smaller amplitude, the period will still be the same. Of course, if you make it too large, then it takes a longer time to complete one full cycle. So the period gets smaller. Well, the period gets larger. The frequency gets smaller. So that is what makes it unharmonic. If you give it an initial speed that is very large, it's definitely not harmonic, not even periodic. Well, almost periodic.
Could you re-explain how you got the second equation?
The second one, well, there's some trigonometric identities, cosine twice some angle. This is twice cosine squared theta minus 1 or 1 minus twice sine squared theta. So this is plus. This is where we derive it. Kinetic energy is 1 over 2 mv squared, the velocity of the object squared. We know how the position changes as a function of time, and hence we know what its velocity changes as a function of time. So when was the last time you went to a playground to swing? You know what a swing is, right? Last summer, okay. Did you swing on your own? How could you accelerate?
actually I couldn't fit.
Okay, you couldn't. Okay, when was the last time that you could fit in a swing and you accelerated on your own?
A couple of years back.
Okay. Somewhere. Okay, don't be shy. I'm sure there are more of you who took the swing. Anyway, the important thing is, how do you accelerate in a swing on your own? Okay, that is what you do. But in terms of physics, what it corresponds to? How do you describe it from a physical perspective, now that we know the enough material to describe it?
By changing moment of inertia.
How do you change your moment of inertia?
By stretching my legs.
So this is basically the equation you have. Okay, one thing is you do change your moment of inertia. The other thing is, but even if you change your moment of inertia, unless you can create a torque, you will not be accelerating. How do you create the torque? Now, while we are thinking, I would like to find a photograph for you. Okay, this is what you are aiming at. So now we are just practicing it with the swing. Of course, you don't have to have these equations, but you have to be able to explain whatever you see around you.
When we first sit on this, our center press is perfectly aligned with it. So when we move our center press, the weight, our weight component is all the fixed point, so it is
So let's see, is this what you are saying? So this is the swing. You are sitting on top of it. Okay. So your center of mass will be more or less somewhere over here. This is your center of mass. Or let me move it slightly upward. This will be where your center of mass will be. And then what you do? You stretch your legs forward, but your body also backward.
If angular velocity is equal to g over r, be changing there.
Okay, hold on. Let's first see how we create the torque. Then I will come to your point. Then what you do is you just lean backwards. And you stretch your legs. You're also holding. Your center of mass will be more or less like here. So this is your center of mass now. So assuming this is your fixed point, this is your rotation axis, what is the direction of the torque? Okay, this is R. Remember, torque is R cross F. Now, one thing to keep in your mind about this cross product. The cross product is perpendicular to both of these vectors, all the time. So if this is R, this is F, R cross F, right-hand rule is out of the screen. So you will get an acceleration in that direction. That means you will have, in the next moment, you will have an angular momentum. You will be moving in the counterclockwise sense. So that's what you also observe. When you lean backwards, the swing will go forward. But then you swing back and forth if you want to accelerate. You just don't lean back, stretch your legs, and stay like that. If you do that, you will be just staying where you are. But you go forward and backward. What is the period? That you go forward and backward. What is your period? Or what is your angular frequency? Well, what you do? You lean backwards, then the swing goes in the forward direction. When it is in the forward direction, you lean forward and you go. You wait until you go back. When it's in the backward, you lean backward. So you are basically following the frequency of the swing. So your period, your angular you don't have an angular frequency because you are not doing harmonic motion, but the period of your motion is equal to the period of the pendulum, which will be just, as your friend has pointed out, the period should be 2 pi square root of L over G. So you have these two oscillatory motions in your system. There is the swing and also your oscillatory motion. And these two motions, we say that you are driving the swing. The driving oscillation, if it coincides with the natural oscillation of the swing, you accelerate forward and back. Your amplitude will build up. Did you try to swing back and forth randomly? Not with this period? Without waiting for the swing? No? Okay, what happened?
After a while, I wasn't going.
You are not oscillating. Or if you just do it randomly, too fast or too slow, you will not build up the amplitude. Only if your oscillation frequency and the frequency of the pendulum they match, you will build up your amplitude. And this matching of these two frequencies is what we call the resonance. You are actually creating a resonance over there. Anyway, we will study the resonance in the next hour. Any questions before we go for a break?
And at some point, the chain of the ring cathode, it was shorter and then it moved vertically for a moment.
That doesn't really have much effect. Okay, see you after 10 minutes.